Welcome back, everyone, again. So, so we have been discussing random walks and its application in biological context, and we have been sort of, learning various underlying mathematical constructs. So, please be patient. I was hoping that today I will discuss a number of empirical examples, but I'm not fully ready to do so. Okay. So today also we will continue a bit more on the theory part. Monday, certainly we will look at the empirical examples of how we actually begin to use these theory that we have been discussing in the class. Okay. So sorry again, I was actually hoping today I will do that, but due to I got really busy in the morning and I didn't have enough time to think through that, and wanted to make some modifications. I didn't have time. Okay. So before I move forward, are there any questions from what we have learned so far? So basically, we have focused on the idea of random walks, and we are thinking of basically the important predictions that it makes and what is the underlying theory. With the, of course, with the basic goal that we will use them in ecological context, and as we will be very soon convinced, it's incredibly, an amazingly useful tool. Okay. So if there are no questions, I will move forward. I have also shared, the Einstein statement of Brownian motion, from Gardner's book. Even if you don't understand all the mathematics, just go through the sort of, the textual parts of it if you can. It might be interesting. Okay. And if you can do the math, do attempt it. I think it's fairly simple. Every step has some very sort of, some sort of an elegance that seems extraordinarily easy, but it also has a lot of underlying sort of, foundational stuff in it. So try to derive on your own as well. Closing the book, once you read, once you understand, try to see if you can reproduce the results entirely on your own. That would be an interesting exercise. Okay. Okay. So we have so discussed random walk so far. I have defined the rules of random walk for discrete time, discrete space case, and we derived some properties. What is the mean displacement of a random walker? We derived what is the mean square displacement, which measures the spread of the random walker from where it began. We have also looked at both the case of unbiased random walk and a biased random walk, right? So we have done all these things, and so though one are microscopic rules. And then those are all microscopic rules and various predictions that arise from them, right? So, for example, the simple rule that probability P with probability 1 minus P, which we also call Q. When P is equal to half, we have an unbiased random walk. Okay. And we also derived some results, which is that mean displacement is equal to 0. That's in the case of P is equal to half, and mean square displacement as a function of time goes as t power is goes as t. Okay. Okay, that goes as t. This is the two predictions we made. Okay. And then, so you can also think of this is, linking from microscopic schools with microscopic rules, which were defined for one time step, right? These were just defined for a single time step. And now this is an arbitrary time, time step t. So you can already saying that, from the microscopic rules, so now we are thinking about what happens over long time scales. And then not only that, we also, because these are all eventually stochastic variables, we have to think in terms of probability. So we discuss this quantity, probability density function. This could be done both in discrete space, discrete time, or continuous space, continuous time. I showed you yesterday that of continuous case. This is the probability density at time t. Okay. I should also say at location x at time t. Okay, that's the probability density. And we showed that this follows basically the diffusion equation. So rate of change of this probability density function, how is this probability density function evolving, is given by this, the elegant diffusion equation. And we also did, I also showed you one simple solution of this for the case when animal starts at a location and then begins to move. Okay, and then you can see that animal was basically at origin at time t0, and then as time passed, right? This is called the initial value problem. X equal to 0 at t is equal to 0 with what did you find? I showed that this p of xt has this feature. It has 1 over square root of dt. It has a prefactor and then an exponential x squared by dt. Okay, I have written this, symbol not equals, but more of symbol called similar symbol to sort of indicate that I have not written all the coefficients correctly. There is either a 2 pi or a 4 pi coefficient here. Likewise, there is either a 2 or a 4 coefficient here. Okay. If you just plug this equation back in the diffusion equation, you will be able to find out what exactly is the coefficients. Okay. So this really told us how the probability of animal being at location X changes with time. Okay. So what do you expect if we wait really, really long time, by the way? Now, animal started at X equal to 0. Wait for really, really long time. What do we expect? It could be anywhere, right, in the entire landscape. And that's precisely what happens. As t increases, there's an exponent, there's an exponential decay here. And there's also 1 over root t, right? So both of the terms are reducing the value of the density. So basically, as t goes to 0, t goes to infinity. So we begin with animal being at origin like this. Sorry, as always, a very horrible graph. Okay. However, if we keep on waiting, it flattens out. And if we wait for infinitely long time, what we basically get is that everywhere this p is basically sort of 0. Okay, meaning it could be anywhere now. Okay, now of course technically if you set t is equal to infinity in this equation, you get p to be 0. Okay, so it means that you cannot really make sense of it anymore completely. Okay, because if the density is 0 everywhere, then it means it's not there, animal is not there anywhere. So when p is equal to infinity, so there is a problem of interpretation, but that apart, it makes perfect sense. Okay, so this is also called a macroscopic description. So here, it is macroscopic in the following sense that, even though we began with discrete rules, right, we sort of ignored the discreteness in the random variables in terms of both space and time. Okay, so we are looking at really large temporal and spatial time scales now. Therefore, we can ignore those details, even if there were some discreteness at the very local scales. And then I'm not looking at an animal anymore. I'm looking at the probability density of where that is. Okay, now this is sort of fundamental to ecology. Often if you think of individual organisms in biology more generally, and of course more specifically in ecology, individuals are discrete entities, right? Individuals are discrete, right? And they are stochastic. And of course, they have spatial extent. However, what we often do is when we write down mathematical theories, we simplify in various ways. Okay, we simplify discreteness, stochastic, and spatial extents to make various approximations to make our analysis manageable. And then from these individual rules, and of course, there are interactions between individuals. You know, in the context of movement, we haven't spoken about interactions yet. Okay, if you put all of that together, what you have is a collective property that determines ecological system. This collective could be, groups, populations, all the way to ecosystems, communities and ecosystems. And when we study this collective, depending on what question we are interested in, we may ignore the space. Okay, so let's think about the type of models we studied in EC 201, the first course on theoretical ecology that I taught last semester, right? So what do we do there? We were mostly studying populations. Okay. Okay. So what was that we were studying? So we know that when populations consist of individuals which are discrete, who have stochastic behaviors, and of course they are spread in space. So how did we, however, write their descriptions? We wrote in the following way, for example, right? We assume that if n is the population density, the rate of change of population density follows some equation. Okay. Let's write the most general form here, f of n. This is the growth function. Okay. And we have now dramatically increased the time scale. So in the Brownian motion case, we were looking at time scales which is less than the lifespan of individuals. Here now we are looking at much longer time scales. Okay. And then we are looking at the processes of birth and death as well, which are again stochastic processes. Okay. And we wrote down an equation which was there any element of stochasticity here? No. So these are called deterministic models. Was there an element of space in them? Again, no, because we lumped all of them into population size n, and we were not worried how they were spread in space. So these are also therefore called, what do we call? There are a non-spatial model. Now, non-spatial models can also come in many ways. Specifically, the most the most predominant one of the non-spatial model that the name requires some justification, which I will come to soon. They are called mean field models. They're also called well-mixed models. So why do we say so? Why do we say they are mean field models or well-mixed models? Let us try to understand that. So now, as you can see now, I'm slowly moving from, I had discussed individual behaviors and their properties so far. I have now moved to populations now. So today's class will be mostly about populations. Okay. So let us go back to the classic model we study in population biology, which is that of logistic population model. So I'm going to assume that you know this. If any of you don't know, please go through the revision materials that I have already posted on Canvas. Okay. So this is the logistic model, continuous time logistic model. So how did we write this down? Can somebody remind me how did we write this down? What was the principle What was the ecological principle that we were using when we were writing this down? Or what was the ecological mechanism or the process that we had in our mind when we wrote this down?
We assume that the per capita growth rate goes down linearly, sir.
May I know your name, please?
Chandan.
Chandan. Okay, excellent, Chandan. Yeah. So per capita growth rate goes linearly with the population. But why does it go down?
Or density.
Because of intraspecific competition.
Absolutely. That's the most accurate description. Let's now discuss all the terms. So what is per capita growth rate? It's nothing but 1 over n dn by dt. So remember that dn by dt is the population growth rate. If I now divide the population growth rate by the entire population size, I have per capita growth rate. It's at the individual level, right? So now this is easy for us to think always. What happens to individual growth rate? What we argued was that if I were to plot, let's call this capital R as a function of n. Okay. Okay, so we considered two simplest scenarios. See, this does not change with n, right? That was the first scenario we considered. And the second and the more realistic scenario was it actually declines with n. Okay. And the first case corresponded to what we called density independent models, right? So this is a density dependent model, but why is there a density dependence? Because as the number of individuals are increasing, the per capita growth rate can't remain same, primarily because the resources will begin to reduce. And when does it happen? If we have strong intraspecific competition, that's one way, the predominant way by which these sorts of density dependence can arise. Okay, that was the idea. And then you have a very simple straight line here. If the value of here is r, and if the value of population size here is k, with this we actually get this equation: dn by dt is equal to rn times 1 minus k. Okay, so this is what we call continuous time logistic model. Now here is my question. So I call that these type of models are also called mean field or well mixed models. What is mean field about them, or what is well mixed about them? Let's stick to one of them. What is well mixed about them? Why do you say it's a well mixed model? You may have heard of this term. If you haven't heard of this term, it's fine. But so I'm telling you that these type of models are also called well mixed models. Why do you think so?
Density is same everywhere.
Sorry.
Density is same everywhere.
So one is the assumption is because I have ignored space. Thing is, I'm not saying density is same everywhere. I just ignored space, right? Okay. So one way to sort of reconcile if there was indeed a space is to assume that it's a homogeneous system in space, right? So therefore the density is same. Okay, that's one way. Anything else? Why does it require mixing? Are you saying that any differences that happen will get mixed? Is it what the idea is?
I think you assume each individual is identical, and that's why that's sort of.
But what does it have to do with well mixed? That would be, no variation.
Otherwise, there can be some kind of clustering, like local interactions.
Mm-hmm. Oh, okay. Is it not possible to have individuals who are different yet have a well mixed system?
We can have.
Hmm?
We can have that system.
Mm-hmm. So maybe there is some simpler reason why they're called well mixed systems or mean field systems. So the basic idea is as follows. Let's think of this growth rate. Just remember that R is basically a descriptor of the individual property, right? So this is an individual level property, right? Average individual level property. Okay, that's all. It's always in averages we are thinking of. Okay. Whereas the x-axis is the population measure. population density. So what does this say? If the population size, let's say somewhere here, some k by 4, the growth rate of an individual, okay, will be given by the total population size in the entire system. Is that correct? In the real world? And or rather, when is it correct? An individual, basically the assumption here, an implicit assumption we never made very clear, which I'm not trying to make. No. Individual level property, although it's an average, okay, depends on total population. Size n. Isn't that right? So imagine there are some, let's say you might be doing experiments with, let's say, bacteria. Let's say you grow them on some Petri plate, right? That could be one context to think about. Other extreme could be think of some big animal, like maybe elephants, okay, and again think.
So are the resources also homogeneously distributed so that we get a overall effect on an individual?
One is about resources, okay. What else? Something, think about the interactions again, because we are not explicitly modeling resources here, right? We're only modeling the, competition, effect of competition, right? So here is one question. There, imagine, homogeneity is something you have all rightly captured, okay? Homogeneity is one thing you have rightly captured. Even in a homogeneous population, let's say, let's think of a sort of a landscape like this. There is this individual whose property you're trying to measure.
Would it be correct to say?
All
Is it
around here.
isotropicness?
Say that again.
The isotropy that exists, like they interact with all the individuals surrounding them in the same way.
Okay, yeah, getting closer, but not quite the point that I am trying. Maybe that's, you may all have what I have in my mind, but maybe not. Maybe in slightly different words.
All individuals interact with all individuals. Is it something like that?
That's right. That that's getting very, very close. Okay. So now okay, here is the individual of our interest. We want to measure its property, in this case, the birth or death probability, right? Total population in this entire landscape is n. But what do you think the birth and death of this will depend on? Will it depend on the total population here, or will it depend on some neighborhood? What is more likely?
Neighborhood.
The local neighborhood.
Neighborhood, right? Okay, exactly, right? So, although the neighborhood is the one that we all think is a better determinant of what determines individual properties, we are assuming that it's a total population size. Okay. In other words, now imagine that, if I were to now spatially, identify densities, let's say there is some density n that depends on x. Okay. There is value of, let's denote it by small n. Okay. Population size depends on x, but the total population size is n of x. We have summed over all locations, right? So, so the R, technically, R individual, if R is present in X, this will be a function of, this is most likely a function of the local density, right? This is one assumption, but what we are doing when we write down this model is that this R does not depend on X at all, right? The space is ignored, and it actually is a function of n. We can say this is closer to reality, and this is the approximation we made. Okay. So we have ignored space, that is very evident. What have we done from here to here, n small n x to capital N? We have basically said that if you were to think of capital N as the average, I can also divide n by the the area of the landscape. Okay, then what we have basically done is the local growth properties depend on the mean property of the entire landscape. Okay, local growth rate depends on mean. Whether you write mean or total is not particularly important, but in the mean density of the entire. This is why we also call them mean field models. Okay, so the word field comes from physics, where you usually study various fields, like electric field, magnetic field, gravitational fields, and so on. Okay. So that's the reason we also call these type of models mean field models. There is another model, there's another name which I mentioned. They are also called, what was that? That explains this now. What about the well-mixed models? This, I think, refers to what I think, if I'm right, Bevan said this, if I could recognize his voice correctly. This is what Bevan was saying. So when is this again true? If you think about this, when is this now true? When is this a reasonable approximation rather, right? So one way to think about this is, if any two individuals in the entire landscape are equally likely to interact independent of distance between them. Okay, that is when the mean field models are valid. If any two individuals have equal probability of interaction, then that's when the mean field approximation holds true, and therefore we call them well-mixed models. And well-mixed model name also comes literally from the way people used to do experiments. You may have heard of something called chemostat and all, right? Where you have a beaker which has some resource inputs and outputs, and you study some culture of some organism growing. And the idea is that that medium is well mixed constantly. It's also called well stirred system, literally stirring well. And when you stir well, no individual spatial location now becomes unique or important, because they're all now all over the place. And therefore, again, that's another case when these kind of approximations are valid. Okay, so that's the context of how we study these simple models. Okay. Okay. So do you have any questions on this?
So when we say about that well-stirred system, so this property satisfies, right? So the last one that you spoke about, that there is equal probability of interaction of any two individuals.
If you stir well, indeed, yes. The idea you stir well so that the probability of any two individuals, independent of the distance, have equal probability of interaction. Of course, technically you don't need that exact condition to be satisfied for the mean field models to be valid. Mean field models are, people use them because they provide a first-hand intuition of what's probably happening in the system. Okay, they're really useful mathematical simplifications. Okay, but strictly speaking, that's when they become correct.
Okay.
Okay. Okay. So now let's
But just one doubt.
Yeah.
In a ecosystem, but this can't be true, right?
Oh, absolutely. This is not true. You're right.
It can't be true.
Yeah, so it can be true, it may not be true. So just think about when it may be true. Because I've always used, see, no assumption is true in a real ecosystem, right? Something I have repeatedly emphasized. There's not a single assumption that is true, but some are more useful than others. Okay. So in some cases, these will be useful. For example, the classic experiments that you do in microbiology, I think, right? The growth experiments. That's there's a the growth curve experiments. There, mean field approximation is a reasonable approximation. Now, can you give me another simple microbiology of experiment, which is also a pretty hot research topic over the last decade, where it's not true?
Biofilms?
Exactly, yeah. Biofilms are the classic, really good example where this is not true anymore. Okay, because the spatial separation, the spatial spread really becomes very, very important there. That's a very good answer. And that's also precisely what I had in my mind. Okay. Shall I move on now? So now, so what I will now do is I will just recap a little bit of the basic analysis we learned in population dynamics. Okay, because we will make them more realistic. That's the goal. Okay. When I say population models, I actually mean the mean field population models. Okay. So the most general form for a single species will be of this form, right? Okay. So the growth rate of change of population is given by f of n. And how do we understand this? We understand this in terms of equilibrium and stability. Okay. So what is an equilibrium? Equilibrium population, okay, is a population size where the growth rate becomes 0. And when this happens, how do we find out them? We find out them by setting the function f to 0. So the roots of this function will give me all equilibrium values. Okay. So, and we consider only positive values to look at positive, to look at population sizes. And then just because, and we also learned about the idea of stability. So idea of stability is that, if I make a perturbation from the equilibrium, will the perturbation explode or will the perturbation decay itself? So for any equilibrium, we know that by characterizing this, if this is 0, less than 0, that means it is a stable equilibrium. If f prime n star is greater than 0, we call them unstable equilibrium. Let us now apply this to two models. Okay. The first model is the topologistic model. Okay. So where R is the intrinsic growth rate and K is the carrying capacity. Okay. So what are the two equilibriums? We find the equilibrium by setting the right hand side to 0. And that will lead us to either n star is equal to 0, which is basically like, an extinction equilibrium. You can think of it as local extinction because extinction cannot ever recover. The carrying capacity. Okay. Now, there are two equilibrium, which means that if the population ever ends up in either of them, they will just stay there forever. The question is, what happens to perturbations? To do that, we look at what is called stability, because the perturbations are always happening in real systems. Okay, let's consider the n star is equal to 0 equilibrium. For that, we need to find f prime of n. F prime of n is dn by d by dn of Rn times 1 minus n by k. Okay, if you do the derivative, what you will find is it's basically R times 2Rn by k. R. That's right. So let's look at the stability for n star is equal to 0. What we will find is that f prime of n star is equal to 0 will be R. Okay, now let us assume that intrinsic growth rate is positive. Okay, if intrinsic growth rate is positive, what does that mean? This means that n star is equal to 0. It's an unstable. Clear to everyone? So what does that mean? Imagine there was maybe an island, as you know, that these models can be applied to some limited contexts, right? Because we assume that there is no migration, immigration. Therefore, we should think of this as maybe an island of some, isolated landscape. Let's say it has no population density of the species that you're interested in. However, if you now introduce a small number of them, because the intrinsic growth rate of that population of the species in this landscape is positive, they will quickly begin to grow. Therefore, n star is equal to 0 is unstable. What about this? Of course, the converse holds true. If R is less than 0, the exact opposite will be true, which means that n star will be equal to 0 will be stable. Again, let's calculate f prime n star at k. If I now substitute n is equal to k in this equation, what do we get? We get R minus 2R k by k, that is minus R. Right? Now, again, if R is greater than 0, this implies that this entire f prime of k is less than 0. This means that k, the carrying capacity is a stable equilibrium. So this means that if the population was at carrying capacity, the perturbations that, of course, as we know, always happens in ecosystems, natural perturbations. It could be because of various types of environmental stochasticity, right, and other unknown factors. That doesn't kill the population. Any perturbation that happens will recover back to the carrying capacity. Okay, but remember that this entire stability analysis is true only for what is the caveat?
Only for small perturbation.
Exactly. Only for small perturbations. Okay, that's the caveat. And therefore, the stability analysis is also called linear stability analysis, because when we derive the condition for stability, we considered only the linear term in the Taylor series expansion. Any questions so far? So for those of you who were not present in the previous class, I had asked you to go through various videos. In fact, I told you don't have to go through the entire last year's course, but I have also given links for a much shorter version of the same. If you have gone through this, all of this, hopefully you should be clear. If not, let me know. I can make sure I can give you additional materials to catch up. So let's now look at one more model. Now, let's how do we build models? We have discussed this, right? Now we have discussed that we write, R of n, the per capita growth rate, and we write this as a function of n. Okay. When we consider only intra-specific competition, what did we do? We basically considered a linear decay of this, right? Now let's consider a slightly more complex scenario where this following scenario, think of species where when they're small in numbers, they may have difficulty in finding mates. Think of species which are group living. When they are small in numbers, they're unable to survive as well as they did, compared to when they were in groups. Okay, and of course, for the formation of groups, you do need a sufficiently large number of individuals. Okay, so if you consider these kind of scenarios, one may argue that, for example, if the broad argument is that if the species numbers are less than some threshold value, let's call them NC, the per capita growth rate. So in the previous case, it was all about resources, right? Now we are bringing things like, mating, things like, maybe social behavior and grouping behavior. Okay, when that becomes important, it's possible that even when there are abundant amount of resources, the other ecological factors are not conducive for individual survival and reproduction. In such a case, what you may have is that you may have a negative growth per capita growth rate until you reach a population density NC. Okay. And it becomes positive only after that. It actually continues to increase, because more numbers the merrier. The species really loves being in large numbers. Okay. However, there is a limit beyond which what could happen? Beyond which competition eventually takes over. Okay, so initial growth phase increases in the per capita growth rate could be attributed to the fact that they have better mating opportunities. As they increase in numbers, they have better survival chances. Okay, so this could be possibly driven by better survival and mating with N. On the other hand, this could be again the same intraspecific competition. So remember that whatever the ecological factors that can present, eventually intraspecific competition will become a limiting factor for any population to grow. It can't just keep on growing forever. Okay, if you include these two, you now have a much more interesting scenario. Okay, I don't know if I actually gave this as an assignment question in the previous course. I may have given, did I? Or maybe an exam question.
No.
Oh, I did not. Okay. Okay, so this is, now there are many ways to write this mathematically. Remember that, dn by dt, 1 over n dn by dt is equal to r of n, right? Per capita growth rate. So therefore, dn by dt is n times r of n. Now, of course, there are many mathematical functional forms that could, mimic this. So one of the simplest one would be this. The carrying capacity sort of things continues to hold the exactly same way. Something like, 1 minus n by k, that continues to hold true, because this eventually drives you to the negative values when n is very, very large. However, when n is small, this entire thing is positive, right? So you want something that makes it negative, and that can happen by something like this, n minus nc. Okay, so if n is less than nc, this term is negative, therefore the entire term becomes negative. Okay, however, n is greater than nc, now the entire term is positive, but eventually, this term will, make it negative for n greater than k. So where nc is less than k. Okay. So we can write this kind of a model now. So dn by dt is equal to Rn n minus nc minus n by k. Okay. Okay, so you can also write down, you can also plot, remember the stability analysis we did in the previous course. The basic stability analysis, we can do it in two ways, right? We can solve all the roots and then find the, the derivative. That's a mathematical way, but we can also do this in graph, right? So I can just plot f as a function of n. So how will the f look like in this case? When n is equal, so look at the per capita growth rate. Per capita growth rate is negative, increases and comes down. What about the total growth rate? So we just have to multiply this function by n. Okay. So convince yourself the following is correct. This is how it will look like. This is 0. This is nc. This is k. So you have this function already. Multiplying it by n doesn't change these two equilibrium, right? Because whatever is 0 will always remain 0. That can never change. Only non-zero parts will change. Okay. So this is the non-zero part. How will this change? Because I'm multiplying it by n, it will undergo some changes. And all that you need to understand is that when n is equal to 0, I'm multiplying this function with 0. Okay, at n is equal to 0. Therefore, this has to be true. So therefore, now you have to somehow connect these two, and this is the only way to connect. Okay, and on the other side, the sign is not changing, only magnitude will change. Again, the same for n greater than k. Okay, so now is this fine with everyone, or do you need some time to process this? So one way to think about this, when n is positive but small, this is negative, this is positive, this is positive, right? If you think of three terms, positive, 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 and negative. Product of positive, positive, negative will be negative. So in this range, it has to be negative. Okay. And we know that n is equal to 0 means the entire thing becomes 0, and n is equal to nc means the entire thing becomes 0. So you have to connect 0 to 0, but via negative values. And likewise, again, we know it has to be 0 at nc and again k, and every one of them is positive. This is positive, this is positive, this is positive. Therefore, it has to be like this. Okay. So one way to plot functions, by the way, is always this. Find all the roots, and now between two roots, check the sign of the function, and then make connections. That will get a qualitative picture of any functions. Okay, this is where we are. So now, there are three roots, 0, nc, and k, three equilibrium values. So how do we find stability? Let's make a small perturbation from 0. What happens? A small perturbation. What's the growth rate when there is a small perturbation now? It's a negative growth rate, which means the population will die off. So any perturbation you make from 0 dies off back to 0. So therefore, 0 is a stable equilibrium. Unlike the logistic model. Okay. In fact, that's the way we designed the model. So we should not be surprised at all. That's precisely how we designed it. Likewise, what about K? Think of it. Again, basically any perturbation I make to the right, negative growth rate, that will die. Any perturbation I make to the left, there's a positive growth rate, so it actually increases. So again, this is a stable equilibrium. What about the intermediate one? NC? Unstable. Okay. So because any perturbation I make to right, there is a positive growth rate, it goes away. Any perturbation I make to the left goes away. Okay. So there's actually a mathematical theorem that says that for 1D models of this type, one population models in continuous time, the stability will alternate Stable, unstable, stable. So the next equilibrium, if it exists, must necessarily be unstable. Of course, if this model doesn't have any other equilibrium, so we stop here. So it has to alternate. So technically, if you find the stability of one, you know the stability of everything else, because they have to literally alternate. But that's true only in one variable models, one population size models. Okay. So this model is also called alley effect model. So alley effect is a very important concept in ecology, which basically says that unless the population has reached a certain minimum threshold, the population will collapse for reasons such as the ones that I mentioned. Again, any questions on this model and the analysis as well?
So does this model assume that NC should be much less than K, like to fit better to the graph that we have drawn?
Say it again.
So here we just mentioned NC should be less than K, right? Should there be more stronger than this condition that this should be much smaller than, or if you want a linear or say different types of curves at the starting only?
Yeah, so you can work on those. Is it NC much smaller or greater, but the qualitative features will remain same.
Yes.
It doesn't matter where exactly NC is between 0 and K, right?
Okay.
So but the qualitative features will remain same. So this is also an example of a system with multiple stable states, right? Multiple stable populations. Of course, here the one of them is 0 and K. Okay. Not only that, what's the other feature of this model? Whenever you have multiple stable states, what happens? What's an immediate consequence? So depending on whether the initial populations, if imagine the initial population size was here. So this was again, let's say if you're trying introduction of some species, if the initial population size was here, where will the population go? What will happen?
0.
It will go towards 0, right? Go towards extinction. However, if it was here, what happens?
It survives and
survives. So there is a initial condition dependence. Dependent on a final state. Okay. Okay. So this was basically meant to revise the basics of population dynamics. Okay, the basic concepts, at least single species. We'll do 2 species later. So what do we do with this? Why are we doing this? Now we want to incorporate the goals of this course, which is to incorporate the effects of stochasticity and space, right? That is not, so we have neither of it in this. It is a mean field deterministic model. So both the logistic model and the alley effect model, they're both mean field deterministic models. In fact, I should say, go back to this and say, I have to say mean field, not just mean field. I'm looking at mean field deterministic models. Okay, so we have studied it so far. Okay. Let's now see how we can do better. Okay. So the first goal we will do now is incorporating space. So let's try to draw some cartoon picture of a landscape. Okay. So idea is, when we try to extend mathematical models from what we know, it's useful to keep what we know. Okay. That way we sort of fall back on what all we have done so far. Okay. So that's the approach we are taking today. We'll also take a much more radical approach a bit later. Okay. So let us do the following. We know that ecological landscapes are spatial, ecological systems are spatially explicit. So what we shall do is assume that the ecological population can be assumed to consist of assumed to exist in this on this landscape, and this landscape itself can be thought of as some sort of grids. There's a huge landscape. Think of now. Okay, let's say this is, I have written two-dimensional two-dimensional grid here. Okay, but it could be one dimension, it could be also three dimensional. So let's say this is the grid I'm interested in. Let's say the location of this grid is X. Okay, so and then let's assume that N of X is the population density at location X. Is it fine? When I say at X, I actually mean that I'm only thinking of this grid here now. Okay. Okay. Now, for the sake of argument, let us assume that this NX population density is independent of everybody else. Okay. How would an equation for that look like? Consider what we call, a very extreme case where NX does not interact with outside its grid. If so, what's the population growth equation going to be for this?
Can't we use the logistic model with the local population?
Okay, excellent. So we can right, where K is the carrying capacity of X, the grid X. Okay. Is that fine with everyone? Any doubts on this? Okay, great. So if there was no interaction with the world, we know how to write the equation. Okay, and this could be written for any X. X could be anyone in this entire landscape, right? If every grid was an independent grid that did not interact outside its grid, we have an equation like this. Okay. Now let us relax that now. Now assume something. So what's the process that can happen that across grids?
There can be migrations.
Exactly, right? Anything else that can happen? Anything else that can happen?
That resource sharing among the grids,
Sharing what, sorry?
resources, or is that
Let us not explicitly model resources for the time being, okay?
Okay.
So the migration is, as you rightly said, the most fundamental process that can happen across the grid spaces, right? So what are all that can happen along migration? Let's again think of it in a one-dimensional world to make life a bit easy, okay? Let's say this is X. Let's say this is ith grid along X, okay? So let's say we have some population here, which is Ni. Let's say this is the I plus 1 at the grid. And we have I minus 1 at the grid. Okay. Now, the population here, we have said that in the absence of migration will look like this, right? Now, in the presence of grid, the population will now again change because of migration. So why would it change, by the way? It would change because individuals from here can come here, right? Likewise, individuals can come from here, can come here. Do you agree with that? So you can call that, inflow. So the inflow,
similar to random walk, right?
huh?
So now it will be similar to random walk.
Absolutely right. Yeah, very good. This was it, Bevan, by the way?
Yeah.
I think of all people, I recognize your voice really well. Great. That's absolutely right. Okay. So here is the small difference though. So when we were writing the random walk model, right, we were writing for individuals. Now we are looking at at each grid, there is a small population. Okay. Okay. So we will make that connection very clear now. If you now assume that every individual in each grid randomly decides. So there are some individuals here, no, let's say N, whatever. Okay. Something like this. So every individual here randomly decides to go this way or this way. Okay. Likewise, every individual here decides to go randomly this way or this way. Okay. And likewise, the same here. If this is happening, what do you think the inflow minus? Okay, let's call let's call the total flow rate. How will that now look, right? If every individual is randomly deciding to go this way or this way, what proportion will go this way? That will be n I minus 1 divided by 2, right? That's the positive flow, right? Because half of them would have gone the other way around. And likewise from here, n I plus 1 by 2. And of course, everybody from here, they're all migrating. So flow rate will be basically, I wouldn't say equal to, it will be proportional to this quantity. Okay, this is basically, if you were to now write this in the, you can write this as I plus 1, I minus 1 in discrete terms, right? I can also write this as x, x plus delta x and x minus delta x, right? So if I write in this fashion, this will basically become n of x minus delta x at time t plus n x minus delta x at time t minus nx at time t, right? This is what the flow rate will be, right? And this is precisely the set of terms we had when we wrote down the diffusion equation, right? When you were deriving the probability density of how individuals are moving, because p of x minus delta x time t, p of x plus x delta time t, and minus 2p of x. Okay, this is for a given discrete time unit delta t. Now, if you look at the rate of change, what we found was this was nothing but a diffusion equation. So therefore, The only difference is P has now become N. So basically flow rate in terms of N, basically, if you now jiggle with all the delta T's and so on and so forth, what will that now become? Do you agree with that? Flow rate, you can say this is the migration. Is everyone happy with this? Any questions?
So actually, I'm a bit confused. Earlier we were saying N is the density, right?
Yeah.
So, but while writing this, so flow rate we considered as the animal numbers that are moving either left or right.
No, it could still be density. Yeah, there's no problem. You can just divide everything by A in the area of each grid. That's what isn't that right?
Okay.
So I'm using the same dimension that we were using here. Okay.
Okay.
So one way to think about this is the following. We know how the probability density changes over time if it was a single individual. That's the diffusion equation, right? That's for a single individual. All that you now need to do is to convert this to a, not one, but many, is to multiply it by the overall concentration. The equation will be true. This is basically what I have now done, is basically exactly what you do in, I think what's called fixed law, right? Where there is a concentration. How does concentration of various chemicals and so on, how does that diffuse? That's precisely what we have done. Okay. So now if you now incorporate, so here is the fascinating thing, right? The migration was happening. Remember the time scales, huh? These are all small. Migration or movement, okay, which are small time scales. If it continues across lifetime, what we have here is a cross generational time scale equation. If we assume that the two processes can be reconciled, what we can now write is basically for each grid, you can write down an equation like this. Partial derivative of n with respect to time. The first term captures basically the birth and death processes because of intraspecific competition for resources. And the second term captures how the movement is affecting the change in the population density. This is also called, so this part is called the reaction part. So this name reaction comes from chemical reaction literature. This is called the diffusion, obviously. And put together, these are called reaction, diffusion equations, or reaction diffusion model in this case. Okay. And this specific model where we have a reaction term is a logistic term, and we have a diffusion term, which is also called Fisher equation. So Fisher, as you know, was the same statistician, population dynamics guy, and Kolmogorov was a probability theory guy. I don't entirely know the historical ways in which they were developed. I don't know if they developed independently or in collaborative way. I don't know exactly what happened. I should look up actually. And Fisher was basically thinking of this as studying how gene flow happens in population. So a new mutant strain has arrived. Has now come out. Let's say it has an R greater than 0. Okay, it has, you can now think of, let's say there's a landscape. There is some existing mutant strain, but imagine there is some mutant strain in some edge of the population. How does that now flow to the entire population? What are the properties of this flow? That was the question he was trying to understand in the 1950s. Okay. Fisher-Kolmogorov equation, and then there are the other persons also who are studying these kind of equations in various population biological contexts. Although this equation looks complex, it has a history of more than 50 years, almost 70 years. So is at least the modeling framework clear? Now we will get to how to solve this equation soon, but is the idea clear? Isn't it very interesting that we started off with random walk and we ended up with writing an equation for populations?
So here we are, time scale is being set by R and D units, right?
Absolutely, yes, absolutely. The diffusive time scale, the time scale in which what we call population front will move. And there is also a birth and death time scale that the R determines. Absolutely, yes.
Okay. And they can be of, say, any arbitrary scales, right? They
Yes,
don't
absolutely.
have to be either small or greater than other.
Absolutely. If you think of, depending on the species of interest, there are some species who hardly move, right? So think of, can you give me examples of both extremes, where R is much greater than D and vice versa? Can some of you give some examples?
For corals, for instance, R would be much greater than D.
Okay. What else?
And for elephants, D would be greater than R.
Okay. Yeah, they move a lot in the entire landscape. Absolutely. Yes. Yeah. Any more examples? What about, let's say, in the biofilm growth? They may even be comparable, right? Because every reproduction, if it's going to a new location nearby, the diffusion itself is a consequence of birth and death. They may even be comparable in some of those cases. I'm not saying in all cases, in some of those cases. And what about plants?
Yeah, I was thinking about plants. So plants, D will be lesser, right?
Absolutely. D actually will be lesser. Absolutely right. Yeah. Because the seeds disperse once in a lifetime, right? Literally. So, they may disperse many times, but the survival effectively will be still only a few times in the entire lifetime. So they are comparable, or D may be probably even lesser. So yeah, that's good. Yeah. So, it's, whenever we write mathematical models, it's really important to understand the intrinsic scales of the system. Okay. As is something ecologists sort of always think about, and it's equally important when we're writing equation, even more important. You got to have some sense of, for your system, what are the time scales, what are the length scales that you have in your system, right? So both of them are really, really crucial and important. Okay. Okay. So now we have actually married birth and death process with movement, and we have a reaction diffusion equation. So can we, I will not go into solving this today, but can you make a guess for possible solution? Do you understand what's the solution? So you remember, okay, now let's go back to the revision of this. How did we approach, any more questions on the formalism and how we think about this before we go to a solution of this? Because it's important to think through all the issues. The mathematics will slowly follow.
the assumption that we started with considering of a grid, so that's no longer an important condition, right? So grid can be arbitrary small or large.
True. Yeah, absolutely. Yeah. So the thing is, it's always a bit challenging. We start with this microscopic thinking, right? And then when you come to continuum, it's all called continuum descriptions because now it's continuous in space and time. Okay, some things become a bit tricky to define. Now, what is K now? K was defined for the grid when we wrote down, right? Now, when we came to continuum descriptions, delta x could be as small as we can, like, right? So K effectively is not now a number for a grid of given size. It's now a density again, just like n itself is a density, right? Okay. But there are some even more difficult subtle issues that come up when you go from discrete to continuum.
So the reaction term
It not be the carrying capacity of the entire landscape in net terms. Actually, it's better to think of them as densities now. Sorry, go ahead.
No, I was just asking the reaction term, like it is still deterministic, right?
This is all deterministic. Absolutely right. Yes. So we haven't. So what have we done now? We have accounted for.
But the diffusion term is stochastic, right? Like we can go.
So the
direction can change.
Here is the thing. So the locally birth and death is stochastic. Movement is stochastic. At the population level description that we are writing, which is called reaction diffusion equation, everything is deterministic. So we have moved away from it, because the basic idea is when we are now dealing with large numbers, okay, and with large, space and time scales, the averages are great. Okay. So I'm not looking at individual animal dispersing in a stochastic way anymore. Even if that is happening, at the coarse scale, the effect is deterministic. That's the basic idea.
Okay.
And this basically comes because the flow rate that we have considered is mean flow rate, right?
Is that mean flow rate?
So we wrote flow rate, right, with the addition and of while you were describing one day.
It is a consequence of lot of individuals moving. Therefore, it doesn't mean that. Yeah, right, yeah.
Yes.
Yeah. See, another way to now that the assignment deadline is over, I can discuss the first question in the assignment. No, you all see the Galton board, the videos and so on.
Yes.
You see what happens when that fellow drops it, right? So every ball that is falling off, at every step it is falling down, is getting hit by a rod, right? And what happens at that stage? It either moves to left or right. So every one of them is doing a random movement. Okay, we're all able to understand it, by the way. Do you have any questions on that? Okay, but however, if you look at the population profile, okay, not one ball anymore, but all of them put together, it actually it evolves exactly like the diffusion equation. So the individual randomness gets, becomes an envelope at the level of population. So what you should think of is, every ball dropping is basically a random walk, but what you see as the outcome in the bottom of the board, right? That's the population profile. Does it make sense? And what we have done here is, in this diffusion equation, is a population profile when everybody is doing a random walk. And of course, when you think of chemical systems and physical systems, this diffusion, is consequence of how many molecules, which are all randomly moving. How many molecules are there?
They are in moles.
Right. What is the number?
10 raised power 23.
10 power 23 of that order, right?
Yes.
Therefore, this description is incredibly accurate. Okay. However, when we think of thousands of animals, maybe, when we are less than, I would say, 1 million, maybe even, 1 million may also be very large. something like, we are probably in the thousands to 1 lakh, that intermediate range. This is a reasonable approximation, but there will be, inaccuracies in the way it captures it. Okay. Whereas, 1 million and above, usually these approximations work really great. And of course, if you have less than 1,000, this diffusion approximation becomes pretty bad. At the level of envelope, I mean, if you do lots of ensemble average, it would still be fine though. Okay, so it's important to understand and think through these issues. When exactly are assumptions valid? And it's a non-trivial problem, by the way. Since there is no easy answer to this question, it depends on the exact microscopic rules and how we implement them. All those things become very important. Any more questions? Okay, if there are no more questions, I'll just do one last bit today before we close the class. So let's think of some possible solution. Okay, let's interpret this in a general way, not just for the Fisher-Kolmogorov model. So this is a partial differential equation. We have a reaction term. And we have what we call the diffusion term. Let's recall that when we had a mean field model, we found equilibrium by how? We found equilibrium by setting f is equal to equilibrium solutions, right? Now, I have a question. Can we define an equilibrium here for this system now that we have a more complex term on the right-hand side? How can we still define? Can we still define an equilibrium?
Yes.
What would that be? Dou n by dou t
Equals
0, right? For all x, right? Is that right? Okay. So that we can define an equilibrium. So I have a following question now. Are mean field equilibrium, let me write them as MF, okay? MF equilibrium still valid? So let's say I find some solutions of n from this solving only this part, reaction part. Are they still valid for the complete spatial model, the reaction diffusion model?
No.
No. Why not?
Because we need to then solve this differential equation, right? The second order differential equation.
Yeah. So let's think about this as an example to make our life easy. Okay. Always think of, visualize this. Otherwise, these equations alone might be quite intimidating. Think of this again. Go back to the grid picture. Okay. So we had this focal grid, right? Okay. And again, think of logistic model. Let f of n is equal to Rn 1 minus k. When will this grid be in equilibrium? If it was an independent grid.
When n
At k or 0?
When, sorry?
At
Let's
k
think
and
of
0?
let's think of stable equilibrium for the time.
when n is k or 0.
If you think of stable equilibrium only, right? Then it will be k, right? So
Yes.
for independent grids, right? N star is equal to k is a stable. That means if the population is at carrying capacity locally, it will just remain there forever, right? Now, but the thing is, we also have this term. We also have this diffusion term. Okay, let's now consider this case. Let's say with the diffusion term, what happens? Let's consider this scenario. If nx is equal to k for all x, okay, then what happens? This implies that f of n of x, right, is equal to 0 for, so for every grid now, the reaction, local reaction is basically 0. There is no local growth, right? Because every grid is at carrying capacity. And what about this term now? Diffusion term. If every location has a value of k,
0.
0, right? So therefore, so n by 2 t will be 0 if n of x k for all x. Do you agree?
Yes.
Okay. So is it clear to everyone? By the way, I haven't heard yes or no from anyone else. I think only one person is responding to me.
Yes, it's clear.
So what this basically means, when if n of x equal to k for all x, right? What that basically means, it's also called homogeneous solution. Homogeneous. Solution. What is it called? Homogeneous mean field solution. Homogeneous population at mean field equilibrium, right? Are also equilibrium for reaction diffusion. Okay. Okay, so I will just stop here today. So what is an obvious next question, by the way? So what I have just shown you is, if there is if we now construct a homogeneous solution where every value is same as the mean field equilibrium, every location has the same value as the mean field equilibrium, that will also be an equilibrium, right, for the reaction diffusion system. Are you all convinced with this now? Okay.
So this means k has to be constant for all the
Of course, we haven't, when you wrote down this equation, I did not say k depends on x. Okay. Yeah, k has to be constant. If k is not constant, it means the environmental parameters are varying over space, right? That just becomes a much more difficult problem to deal. It's a heterogeneous system, spatially heterogeneous system. But it's an important problem to look at from an ecological perspective. But do you all agree for this case, homogeneous equilibriums are also equilibriums, right? So what's the next obvious question?
What other solutions are there?
Exactly. Are there other solutions? Are there some non-homogeneous solutions, right? See, you can, I will let you argue that so if you now start this system where every location has exactly same value in the initial time point, will the diffusion term play any role at all? If in the initial time step, if every location has exactly same value, will this term play any role at all?
No.
At any point in time in the future?
No.
Not because it's always zero, right? So it effectively becomes a mean field model. Okay. So homogeneous solutions, if you look at homogeneous solutions, they will be exactly same as the mean field model solutions. Okay. So therefore, the useful question to ask, as rightly was, are there other solutions? But I will even qualify and say, are there some non-homogeneous solutions? Where the entire space does not have same value. Okay, that's the first question. What else? Very interesting question. What else? What do we do usually after doing equilibrium analysis? Finding equilibrium?
Stability.
Stability. So we haven't actually, so I have told you that the homogeneous solutions are also equilibrium when we set them at the mean field values. But what about, are they stable? Have we checked if they're stable? When I say the homogeneous solutions, homogeneous mean field solutions, are they stable? It's not very evident, are they? Is it very evident?
They should be, I guess, because there's no diffusion. So
exactly, diffusion tries to make things spread. Okay, so your answer is right, but we will see if we can prove that mathematically also, but not for today. Okay. So today we'll stop here. So we'll meet on Monday again. So let me know if you have any questions for today's class.
And can we see oscillations in some systems? So certain pattern repeats every time.
That's what I meant by asking this question. Are there some non-homogeneous solutions? That's what we will discover. Okay. Yes, of course, they are possible. So we will find out conditions when we have only homogeneous solutions. We'll find out conditions when there are non-homogeneous solutions. So, but non-homogeneity can happen in space. It can also happen in time. It can happen in both. If it happens only in time, it is same as what we learned in the mean field models. But when it happens in both space and time, that's when we have a lot of interesting. Okay, we'll certainly study the, I don't know if we'll study the temporal patterns as much, but that could be a project that one of you can take up if you like. Any other questions?
you're sharing your entire screen.
Sorry?
Yeah. No, you were sharing another screen.
Oh, is that so?
Yeah.
Okay.
I wanted to ask, so these non-homogeneous solutions, would there be something like what Turing described?
Exactly, yeah.
In such situations where you have like a large space which is made into grids, however small the delta x is it possible for there to be local pockets of equilibrium and rest of them being not in equilibrium?
What do we, okay. Yeah. What local pockets of, that would still be at a spatial level non-equilibrium, right?
Yes, at a spatial level it would be non-equilibrium, but is it possible to identify?
So those kind of things do happen.
Okay.
I mean, to some extent, even in Turing, what somebody else referred to as Turing systems, those do happen.
Okay. we could just constrain to that local and then. Okay.
Yeah. I don't think I fully understood your question. I think, yeah, probably yes. So a lot of interesting solutions do occur. Okay. So I'll stop sharing now if you have no more questions. Okay.
Would that be single species or like multiple species?
Those are all things we will study. Okay. What are the conditions when they happen? What are the conditions when they don't happen? So we look at all of them. Okay.
So this is still different from a agent-based model, right?
Absolutely yes. Absolutely yes. Yes. So the closest to agent-based model that we have studied is the random walk itself. So the random walk is an agent-based model of animal movement.
So because we assume that the entire population is diffusing, it becomes not an agent-based model.
No, we assume that everybody is doing a random walk. Now, if you look at that at the population level, that becomes a non-agent based model.
Okay.
So these are also basically, this is an approximation. These are also called coarse-grained approximations. So coarse-grained approximation means that I'm not interested in a lot of fine-scale details. I want to study population level for now. Okay. When the population is sufficiently large, that's when you have basically these approximations that come up. Okay, which means that they will ignore a lot of details. They will not be able to capture. But agent-based models are also what we will cover in the class. Okay. Any other questions? For example, I asked you to simulate, right? Different types of jump lane distributions. Those are all agent-based models of foraging, for example. Of course, you can make it more complicated there. You can actually include spatial distribution of resources. You can include other, the resources may also have their own birth-death dynamics. Okay, and when an agent goes and consumes the resource, they may die, and you can actually add this kind of stuff. So it is possible to, those are, that's the agent-based model we have done so far. But you can also have agent-based model for the population dynamics, which is, birth and death process. Where for each individual, you define a probability of birth and probability of reproduction and probability of death, as well as movement.
So I have one question. So when we talk about stochasticity, and here we are talking about, say, randomness, if we see at the population level, we get a deterministic output from that.
Yes.
So how we can differentiate the stochastic factor where the solutions are not same every time?
So can you repeat your question? How can we differentiate?
Yes, so we talk about stochastic factor, as you were also saying that if we have animal numbers less than 1,000,
I'm giving you some ballpark numbers. Don't take them seriously.
Yeah, but yeah, in lower numbers the solutions won't be right. So what factors make that differences between the solutions, or make the solution deviate from the actual result?
So it's like, just do a simple experiment. You have a random number generator on your computer, right? On any program you use, R, right? So you take a Gaussian distribution with mean 0 and some variance. And you take 100 random numbers and 25 random numbers. And you sample 25 random numbers and then calculate the mean. So will the computed mean be same as the one you started off with?
No, they won't.
Be a deviation, right? Now, if you do with
Yes.
100, will that be a better
Yes.
estimate? What if it
Yes.
is 10,000?
Much better.
The same thing is happening here.
Okay. Yes.
Okay. Okay, cool then. So shall we stop the class today? I have to go to another meeting now. Okay, and we will meet again on Monday. Okay. Thank you.
Thank you.
Bye.